So if you want an AI to think harder, you usually just have to accept that it's going to, think slower. I mean, we see this all the time with a test time compute models.
Right, where you're waiting seconds or even minutes for an answer.
Exactly. But what if a model could do all of its heavy thinking while you aren't looking, so that the second you ask it a question, the answer is just this instant reflex? Welcome to AI Paper Slop. Today we're breaking down, do language models need sleep? Offline Recurrence for Improved Online Inference by Sang-Yin Lee, Sean McLeish, Tom Goldstein, and Julia Fanti.
And this paper is absolutely fascinating.
It really is. So here's your TLDR right up front. Transformer attention scales quadratically, making long context super expensive. So to fix this, recent frontier models use these hybrid architectures, interleaving standard self-attention with state space models, or SSMs.
Right. Those hybrids basically compress past tokens into fixed-size fast waits to save memory.
Yeah, but here's the catch. They fail completely at deep reasoning over that evicted context. So this paper introduces a solution, and they call it sleep. It's basically a mechanism where a model performs non-dollar offline recurrent, passes over a filled context window to, recursively update its SSM fast waits. And it does this before clearing the KV cache.
Which is brilliant, honestly.
Yeah. And the huge payoff here is that it shifts the massive compute required for deep reasoning entirely to this offline phase. So you preserve this strict, lightning-fast, single forward pass latency during online inference.
I mean, it is a total paradigm shift for compute allocation. If you're training models right now, you are so used to the idea that the hard algorithmic work happens while the model actively generates the next token.
Right, like standard chain of thought.
Exactly.
Yeah.
But this paper argues we should move that heavy lifting offline. So the model prepares its internal state beforehand. That way, inference isn't some long, drawn-out chain of thought. It's just a highly informed, immediate response.
I really want to dig into the hidden flaw of current hybrid models first, though. Because, diagnosing that is kind of the only way to understand why this sleep mechanism is even necessary.
Yeah, we have to look at architectures like Samba or Griffin.
Right. Where you interleave self-attention layers, which give you high-fidelity access to recent tokens, with linear recurrent layers like SSMs to handle the older context.
And, well, the field's consensus on why these hybrid models fail at long context tasks has largely rested on a capacity argument.
Capacity meaning just not enough storage space.
Exactly. The assumption was that if you compress tens of thousands of past tokens into a fixed-size fast-weight matrix, you simply squeeze out too much information.
Right, like the memory capacity is the bottleneck.
That was the running theory, yes.
But wait, if the SSMs physically have enough parameters in their fast weights to, theoretically encode the data, why wouldn't they be able to reason over it?
Well, that's the disconnect the authors point out.
Yeah, I'm just missing the disconnect between storing the tokens and actually using them. Let me try an analogy here. Instead of thinking of it like zipping a file onto a hard drive, maybe it's more like turning a 1,000-page textbook into a one-page cheat sheet.
Oh, that's a much better way to conceptualize it.
Right. Because anyone can instantly copy a textbook to a drive, but if you want to write a highly synthesized, useful cheat sheet, you have to pause, read, process, and connect the concepts.
Synthesizing a cheat sheet takes time. It requires actual compute.
Exactly.
Converting those observed tokens into a useful, queryable, fast-weight memory isn't just about storage. It's a highly non-trivial transformation.
And in standard hybrid models, this compression is just happening in a single linear forward pass.
Which is wild when you think about how we optimize any complex system, like gradient descent, right?
Yeah.
These iterative, repeated updates. You wouldn't expect a single mathematical pass to perfectly compress a complex multi-step reasoning chain into a static matrix.
So the bottleneck isn't the size of the fast weights at all?
No, it's the amount of computation dedicated to forming them.
Okay, so if CPU cycles during memory consolidation are the problem, how do you actually inject more compute without freezing the whole system and just ruining the inference speed?
Well, you can't just stop the generation process.
Right, so let's break down the mechanics of equation 6 and algorithm 1 from the paper. How does sleep actually work?
Imagine the model is processing a massive prompt. It's filling up its KV cache up to a strict token limit. Let's call it $.
Okay, so dollars is our threshold.
Yeah. In a standard hybrid, once you hit the $, the older tokens are roughly compressed into the fast weights, the cache is evicted, and it just keeps reading.
But under this new architecture...
When the cache hits $, the model stops ingesting new tokens entirely. It enters this consolidation phase, it goes to sleep.
Wow, okay. And What is physically happening inside the layers during this sleep phase, like under the hood,
It performs no auto recurrent passes over that accumulated dollar token content.
over and over?
Yeah. And during these loops, it recursively updates the fast weights in the SSM blocks via a learned local rule. It is entirely closed off from the outside world at this point, just refining its internal state.
Hold on. What does learned local rule actually mean in practice? Like, how does that differ from standard attention updates?
So standard attention looks at all tokens simultaneously,
Yeah.
right? It computes a weighted sum. It's parallel, it's global.
Right.
A learned local rule in this context means the model trains a mini algorithm, like a localized neural function that iteratively compresses its own cache.
Oh, I see.
So for each of the dollar passes, it takes its current fast weight state, feeds it back into the SSM block along with the frozen dollar tokens, and applies a nonlinear update to the state matrix.
It's essentially meta learning how to synthesize that one-page cheat sheet we talked about
Yeah.
by reviewing the textbook multiple times.
Exactly. And then, once it finishes those dollar loops, it triggers a hard eviction. The KV cache is just wiped clean.
Just totally empty.
Yes. The model wakes up, the cache is clear for the next chunk of the prompt, but it's now operating with a deeply consolidated fast weight memory.
That makes a lot of sense. And I assume because the architecture is differentiable end to end, the gradients just flow directly through these unrolled recurrent loops during training.
Exactly. The model learns exactly how to optimize its sleep cycles for whatever task it's facing.
You know, the researchers draw a very explicit parallel to biology here, specifically hippocampal replay.
It's such an elegant analog, really. When animals sleep, short-term memories stored in the hippocampus are reactivated.
Right, they get replayed.
Yeah, replayed repeatedly and consolidated into long-term cortical synaptic weights. The animal is completely cut off from external stimuli.
And biologically, the cognitive payoff of this consolidation has to be massive to justify being unconscious and vulnerable in the wild.
Exactly. Here, the KV cache acts as the short-term hippocampus, the fast weights are the long-term cortical synapses, and the nuller offline passes are the sleep phase.
Okay, I want to clarify the test time compute angle here, just for the ML engineers listening, because everyone is looking at models that loop or use dynamic depth during generation, right?
Right, like OpenAI's recent stuff.
Yeah, but all this extra sleep compute happens entirely during the prompt processing phase, right?
That is the critical distinction. Looped inference models scale compute by thinking for a long time right before spitting out a token.
Which severely degrades your time to first token.
Yeah, and your overall generation latency.
Yeah.
But this sleep mechanism spends its extra compute at the boundaries of the prompt processing phase, when the context window fills up.
Oh, so this can easily be hidden asynchronously during pre-filling.
Precisely. Once the prompt is fully digested, generating the actual output tokens requires only a strict single forward pass.
That's huge. Okay, so the theory is really solid, but if you're building frontier models, you need rigorous proof that this actually isolates the reasoning variable.
Yeah, you can't just run it on an MLU and call it a day.
Exactly. Let's look at the synthetic tasks they used for stress testing, starting with Rule 110. For anyone who hasn't worked with it, Rule 110 is a 1D binary cellular automaton.
Synthetic tasks are vital here. If you jump straight to a standard LLM benchmark, you entangle memory retrieval with reasoning depth, and you can't actually prove why a model is failing.
It's just a black box.
Right. Rule 110 is brilliant because predicting the state of the automaton after test steps is mathematically proven to be p-complete.
And why does a task being p-complete matter so much for evaluating a transformer? Like, what does that actually restrict?
Because p-complete tasks mathematically cannot be solved by parallel processing shortcuts.
Oh, interesting.
The state of a cell at time depends entirely on the state of the cells at time minus 1, 1.
Mm-hmm.
So to know the state at step 32, you must sequentially compute all 31 previous steps.
You can't just matrix multiply your way to the end in one step using some clever attention heads.
No, you can't. It forces the model to do genuine step-by-step algorithmic work.
Okay, so they feed the model the initial state of the cells, but they force a hard context eviction every 24 tokens.
Correct. The model sees the board, the KV cache is wiped, and later it has to predict the state after toggle grid transitions. And they use that variable toggle grid as a precise dial for reasoning depth.
So how did the baseline do?
At TFT 3.2.2 toddler, a baseline hybrid model with no offline loops completely fails. It drops to around 10% accuracy, which is basically...
You're just random guessing.
Exactly, just random noise.
Well, but the memory load, like the actual sequence length of the tokens, is identical across these tests, right?
Identical. But when they enable the sleep mechanism with 4 loops, accuracy leaps past 30%.
Wow.
The only difference is the offline compute spent consolidating that memory.
Yeah.
The sleep loops force the fast waits to act as a sequential scratch pad. It's effectively executing the cellular automaton steps offline.
That's crazy. And they also tested this on Depot, right, which is a multi-hop knowledge retrieval task involving directed graphs.
Yeah, introduced by Alan Zhu and Lai. The model reads a shuffled graph, so just a bunch of nodes and edges.
But the graph is fragmented across the context window, right? And then evicted from the KV cache into the fast waits.
Right, and later, the model is queried to find a node that is 2 pops away from a starting point.
Finding a path that is cops away when the graph isn't even in your active memory. That means the fast wait matrix has to somehow encode the entire adjacency matrix of the graph. Imagine a single forward pass just turns that into like a fuzzy blend of noise.
It absolutely does. The baseline model with one loop just stalls out when queried for an answer even 4 hops away.
It just can't form a representation of the graph that supports traversal.
Right, but with 4 sleep loops, the model actively traces those paths offline, updating the fast wait to accurately represent the connections. It successfully scales to solve extreme 16-hop queries.
16 hops?
Yeah. By keeping the sequence length fixed and scaling the hop count $2, they mathematically isolated the reasoning depth.
Proving that the fast waits are actively computing rather than just memorizing token co-occurrences. But, a controlled sandbox is only step one. How does this technique scale to real pre-trained language models on natural language tasks?
Well, they use the GSM Infinite dataset next.
Okay, so GSM Infinite is a brutal stress test. It's a synthetic math reasoning dataset based on GSM 8K, but the problems are artificially stretched to between 2,000 and 3,300 tokens using relevant-looking distractor text.
Right, lots of garbage data. And the difficulty is controlled by the number of arithmetic operations required to solve the problem, up to 8 operations, or op82.
So you are forcing the model to read a 3,000-word math word problem filled with irrelevant junk, and you set the active context window to 2,000 tokens, meaning the first 1,000 tokens, which might contain the first few crucial arithmetic steps, are just evicted into fast waits.
Right, and if those weights are just a linear sum of tokens, the specific numbers just get totally lost.
Because it's like having your scratch pad ripped away mid-problem. The model has to output the final answer instantly, with zero chain of thought, relying entirely on what it compressed into its fast waits.
Exactly the problem. So, they tested this on 2 pre-trained models, JetNematron 2B, which is a hybrid, and RO 1.4B, which is a DEX recurrent model augmented with fast wait memory.
So what happens when you force these models to sleep on complex math?
The gap widens significantly on the hardest problems. On RO 1.4B, for 6 operation problems, using 4 sleep loops, improved accuracy by an astonishing 47%.
47%?
Yeah, jumping from 0.419 to 0.615. And on the absolute hardest 8 operation problems, they still saw a 30% improvement.
What about JetNematron?
JetNematron 2B inherently has more fast wait capacity, so it handled the easier problems pretty well already. But the offline recurrence pushed it through the computational ceiling on the hardest tasks, yielding an 11% improvement on 8 operation tasks with 6 loops.
The paper also explores a sliding window variant, right? Instead of just doing a hard wipe of the KV cache, how does that change the dynamic?
Well, with the hard wipe, the boundary is rigid. But in the sliding window variant, the model retains the most recent -1 tokens. It's similar to standard sliding window attention, so it smooths the transition.
Okay.
They tested this on RO 1.4B, but shrunk the active window down to just 512 tokens.
That's tiny.
Yeah, but the results were massive. With 4 sleep passes, they saw a 52% accuracy improvement, even on simpler 2-operation tasks.
Wow. It shows that when your active window is severely constrained compared to your sequence length, offline loops dramatically improve both deep reasoning and basic context retrieval.
Absolutely.
Okay, we have to address the elephant in the room, though. No architectural improvement in machine learning is free.
Never.
If you are training this, you have to physically pause processing new tokens to run non-null recurrent loops over the current context window. Doesn't that fundamentally break the standard sequence axis parallelism of transformer training? Like normally, GPUs process token 1 and token 100,000 at the exact same time. If window 2 cannot be processed until window 1 has finished its sleep cycles, doesn't that create a massive sequential bottleneck?
It's a great question. The recurrent depth cost does scale roughly linearly with known dollars. So a for-loop model requires 4 times the compute over that specific block during consolidation.
Which sounds like a deal breaker that would just nuke your training throughput.
It does sound like that.
So why isn't it?
Figure 6 in the paper explains the caveat beautifully. GPU utilization is ultimately about arithmetic intensity. If your window size dollars is sufficiently large, and they tested it at 12,000 tokens, the matrix multiplications for those 12,000 tokens across Euler loops are massive enough to keep the tensor cores at 100% capacity.
Oh, I see.
You lose sequence parallelism across the chunk boundaries, sure, but the chunk itself is so large that your GPUs remain completely saturated.
So as long as you chunk your data properly, your H100s are still running at max capacity, and your wall clock time barely dips.
Correct. And this leads to a really profound philosophical takeaway from the authors.
Which is?
For years, the field has been obsessed with fully parallelizing everything purely for hardware efficiency. But attempting to solve deeply sequential reasoning problems with fully parallel computation often leads to brittle shortcut learning.
Right. The model finds a statistical cheat code instead of actually learning the underlying algorithm.
Exactly. By enforcing sequential recurrence through sleep, we force the model to actually do the algorithmic work. Inherently sequential tasks might simply require sequential compute.
That's fascinating. It makes you wonder, if you simulate sleep to refine fast weights via learned recurrence over an existing context, what happens if we simulate dreaming? Like, could future architectures use this offline phase to actively generate their own synthetic imagined trajectories? Could a model optimize its fast weights for edge case scenarios it hasn't even encountered in the prompt yet, simply by dreaming them up during its consolidation phase? Think about that the next time your model stalls out on a massive context window.